Hi, welcome to today's tutorial. Today we will be running through using an OCS in VFD applications. Here's our agenda for today's tutorial. We're going to introduce the topic of OCS and VFDs. We're going to talk about typical applications for these products, why these products are a good fit with each other. We're going to talk about application details. We'll talk about the steps required if you're going to integrate an OCS and a VFD. I'm going to demonstrate an application setup in Cscape, and as per usual, we'll have a live Q&A session at the end. What is an OCS? OCS stands for Operator Control Station. It is the brand name of our all-in-one controller products. An all-in-one controller combines the functionality of control I/O, whether it's local or remote, with a built-in operator interface, along with extensive networking and communications capabilities, all in a single hardware and software package. VFD stands for Variable Frequency Drive, and is a type of drive that's used to control AC motors by varying the frequency supplied to the motor. It's one of the most common components used in electromechanical systems, and is often referred to by different names. Here's a list of applications that you may find VFDs in. Pump control is one of the most popular, fan and blower control, conveyor control for controlling speed, etc., air compressors, winding type applications, in the paper industry, or maybe even the metal industry, injection molding for aluminium, and literally hundreds of other applications as well. It has many uses. So, which brands of VFDs work well with an OCS? Any of the ones here on the screen, and there's even more. Anytime I'm talking about a drive, I'm talking about a general purpose device and not any particular brand. Next, let's talk about why these two components are a great fit. Firstly, they are a complete solution. VFDs are really good at performing motor control, and they can do much more than that. General machine control and coordination between parts is not their strength, but it is something the OCS does extremely well. OCSs complement any weakness of a VFD. Another reason they are the complete solution is the fact that while variable frequency drives have I/O built into them and the ability to interface with some different types of sensors and actuators, they are pretty limited when it comes to I/O. Most variable frequency drive manufacturers don't have a lot of expansion I/O for their drives. The OCS has a wide variety of I/O with the option of additional I/O expansion. There are a lot of sensors that you typically wouldn't find interfacing with a variable frequency drive with an OCS. For example, RTDs and thermocouples are not something you would typically connect directly to a variable frequency drive. Another way that these two are a complete solution is in the operator interface. Almost all VFDs have some level of operator interface. It's not on the level of what is offered within the OCS, where you can choose your screen size from 2 inches to 15 inches, and not just do basic starting and stopping of the motor, controlling speed, and parameters. You can coordinate the entire machine and perform advanced functions like alarm management, trending, and data logging. Next, let's start talking about package size. The OCS combines all these capabilities in one in an incredibly compact package. In the VFD industry, in recent years, the size of the package for the relative capability has gotten significantly smaller. You combine the smaller VFD with the Horner OCS with complete control capability, and you're looking at a very powerful and compact package. Not only has size been shrinking, but prices have been as well. While there are advancements in variable frequency drives and controls, in general, with more power and more functionality, there are also more low-cost products available than ever for both the Horner OCS and VFDs. Now let's talk about connectivity between the OCS and VFDs. There are a variety of ways that you can control a VFD. The most common, outside of manually, is using I/O signals connected to the terminal block or the drive to start, stop, change direction, etc. The OCS has all these signals built in. We've got more than a dozen models that all have enough I/O built in to comfortably control one or more variable frequency drives with I/O alone. You can also control a VFD using RS485 through the Modbus RTU protocol. This feature is standard in every OCS that we sell. We also support some slightly more advanced communication options, including communicating over Ethernet as well as CAN open. There are certainly some advantages to Modbus TCP, and it's a little bit easier to work with than Modbus 485. CAN open has some advantages in terms of some communications rate as well as synchronization functions that you won't find with a typical serial communications protocol. For basic start, stop and speed control capability, you've got the ability to add either a full Ethernet or field bus based network connection or a basic RS485 Modbus RTU connection to not only start and stop the drive and adjust its speed, but also get complete diagnostics such as fault codes, etc. Live statistics like current readings and bus voltages are all available through those connections. Now, let's talk about how you would go about setting up these two components to talk to each other. Here's a map of the application process. These are the steps we're going to go through, and I'll demonstrate the software setup side on the back end. We start by designing the electrical interface, connecting the communications cabling. There will be some parameters that we need to set from the keypad on the VFD, and we'll need to get that user's manual out of the drive and examine the parameter list. Then you'll set up communications on the OCS side of things in Cscape. Lastly, you'll be writing and testing your application from a machine control standpoint, programming any screens that you may want to develop with live data and set point adjustments, etc. If you have any other functions you want to perform, like logging data from the drive, those are also available. Let's start with the electrical interface. For most applications, we recommend that you have at least some signals hardwired between OCS I/O and the VFD. It's not a necessity, but in most applications, it's usually a good idea to have some hardwired dial for things like starting and stopping, etc. You use digital signals for starting, stopping, and changing direction. If possible, you should use PNP type signals. You can use NPN, but PNP is more common and generally is a little easier to use. For controlling motor frequency, if you decide to hardwire that connection, those are usually done with a 4 to 20 milliamp or 0 to 10 volt signal. From an electrical noise standpoint, you're advised to use shielded wiring. With a shielded twisted pair, you would want to handle that shield drain properly by making sure that it is connected to solid earth ground and on one end only. The advantage of 4 to 20 milliamps over 0 to 10 volts is it's a little more noise immune. Another thing that you'll find is for controlling drive speed or drive frequency is that some drives also support a pulse type input, often in a PWM format, where it's looking for a fixed frequency with a variable duty cycle. The next step is to select the communications interface. There's no ironclad requirement that you connect a communications interface between the drive and the OCS. You could strictly use an I/O connection, but we strongly recommend that you connect to the network. Which network you choose is your choice. You could choose the RS485 Modbus, which is built into most drives. You could choose an Ethernet based connection like Modbus TCP, or a field bus type option like CAN open. There are some factors in terms of which network you choose. If cost is the primary driver, then the RS485 Modbus is going to be the approach, because it's built in for free to most drives manufactured. While it's not top of the line from a performance standpoint, it is highly functional. If the application can afford it, then bumping up to Modbus TCP is a good idea. It adds a bit of speed and ease of use. The wiring is simpler as opposed to having to wire up point-to-point wiring. However, you may have a requirement for an Ethernet switch and other components similar to that. If the application can afford it, then I would also recommend going with the Modbus TCP. You might have multiple motors that need some level of synchronization. If that's the scenario, then CAN open is a good choice. CAN open is a very popular field bus network and a lot of drive manufacturers support CAN open. It may be complex, but it is effective. The next step is selecting cabling. This is all about the cabling details for Modbus RTU over RS485, which is the most common electrical interface between a PLC or OCS and VFD. So from an Ethernet standpoint, there's Ethernet type communications cabling, where you wire from each component back to a switch. CAN open is typically a daisy chain using special CAN cabling. So you typically start off with 2 twisted pairs. You're going to use the first pair of wires for the single pair. The RS485 standard instructs you to label the conductors A and B, but not all manufacturers follow that standard. Sometimes they're labeled plus and minus, or D0 and D1. You should also have a third conductor, which can be one of the wires in that second pair to act as your common, as it will allow you to overcome any common mode issues between objects or devices on the network. You're going to daisy chain all of the components on the network. So if it's just an OCS and a single drive, it's basically the equivalent of point-to-point wiring. If you have multiple drives, you're going to be using a daisy chain approach like in the diagram. You need to make sure, whether it's just 2 devices or 4, that the devices on the end of the network are correctly terminated. If the OCS is at one end of the network, then it has the ability for doing termination outside of the cable. So in the case of the XL7 that we're showing, and some other similar products, we have dip switches for setting termination. Some of our other models have a bit that you can set from the system menu, or from your application program, that turns the RS485 termination on and off. The way RS485 half-duplex works is that both devices are using the same pair of wires that signal pair to communicate. At any time, either one device will be communicating with the drives, or neither if you're in between. Sometimes, in a scenario where there's no device that's communicating, you can get some random 1s and 0s that may fly around from time to time when no device is currently driving the communication bus. If that's the case, there is a feature called biasing, which you can turn on in the OCS from the system menu, which will apply a pull-up and a pull-down resistor internally. This will get rid of any random 1s and 0s that are occurring while the network is idle. You should always start with biasing off, and if you need it, you can turn it on later. The next step is setting parameters in the drive to enable or adjust communications. It's possible that the default parameters will work for you, but it doesn't always happen that way, so you'll need to check the drive manual and look for the communication settings that you need to adjust. An example of this would be the ID for Modbus, or the baud rate, which you're going to want the defaults for the drives, and adjust on the OCS side. There will be a number of parameters that you will need to adjust on the drive side from a communication standpoint. There will also be parameters that you need to change that aren't directly related to communications, but are related to where the drive is looking for its start-stop signal, to the terminal, the network, or its own keypad. Almost all drives have parameters that allow you to select where those start-stop signals and speed control signals are coming from, so those will need to be adjusted through drive parameters as well. The next step is to look at the VFD manual and find the parameter list, because there are some parameters you're going to need to find to successfully interface with the drive. It's going to have a whole host of parameters that are accessible, and usually a bulk of them are accessible over the network. You're going to want to be familiar with what parameters that you care about for the application, and which application or which parameters you may want to occasionally access, maybe from an operator interface screen, as opposed to parameters that you want to monitor and or change on a real-time basis. You're also going to want to look at how those parameters are scaled. So let's talk about motor frequency. You'll find variations between manufacturers in how motor frequency is reported. Some manufacturers report in 1/10 of a hertz, some in a 100th of a hertz, and others in different ways. Scaling information is critical so that you can ensure the data that you're reading and writing between the OCS and the drive is accurate. If there's any processing that has to happen, you're going to want to make a note of it. Once again, document the key parameters that you want to work with and that you want to map permanently between the OCS and the drive, and those that you want to access on an occasional basis. Then you're going to continue to look at those parameters from a Modbus perspective. What is the Modbus address that I'm going to use on the OCS side to access these parameters? There's a variety of different ways in which Modbus data is presented in the user's manual. When I show you the OCS configuration, you'll see that we've done our best to try and make what you configure on the OCS side match what the drive has listed in its manual from a Modbus standpoint. We've given you some options on the OCS configuration, but it's important for you to understand what the format looks like. For example, the most common Modbus address style is 5-digit addressing, where the most common parameters, called holding registers, are typically mapped starting at register 40001, 40002, etc. So you may find that in the user's documentation, something that is just a number starting as 0 for the same parameters. Instead of 40001, they may show 0, 1, 2, etc. If they're starting with a 0 base number, it isn't an address per se, but an offset. An offset from the first register in the group, which happens to be the number that gets transmitted over the wire. So again, there are different styles in which drive manufacturers list their Modbus addresses. They could be in decimal, 5-digit modicon, 4-digit offset, etc. The last step is to set up the communications on the OCS side, which I'm going to show you later with Cscape. We're going to start in the hardware configuration, select our serial port, and set it up for Modbus RTU. Then we will do some configuration of the Modbus protocol on the OCS side. Firstly, at the network level, we'll be adjusting baud rates and timeouts, etc. We're going to have some device level configuration for each drive that the OCS is talking to. Then we're going to create what's called a scan list, which is real-time data that the OCS is going to monitor on a continuous basis out of the drive and place in local OCS variable space or register space so that you can access it anytime you want. If you ever want to change it and it's a writable parameter, those are the steps involved. The next step is getting the application going. You're probably going to need logic for starting and stopping things. You'll need to know what the algorithm is for adjusting speed, what happens when the drive faults, where's that data going to come in, etc. From a communication standpoint, what do you want to have happen in that scenario? On the operator interface side of the application, where am I going to monitor status of communications? What screens am I going to create to adjust parameters in the drive? And then what other functions do I want to perform in addition to basic control and operator interface? It's time to move on to a Cscape live demonstration. Here we have a demo program. This is a typical program that we might send to a customer who's interfacing with a particular drive to try and help them get started with communicating with the drive. This is an XL7 controller with a VFD from ABB. The first step is to go to the hardware configuration, but I'm going to go a little backwards and show you one of my screens that I've got set up for diagnostic purposes to give you an idea of the type of data that we're going to be accessing, as well as the diagnostics for communications. In this example, I'm not using I/O signals to start and stop the drive. I'm actually using the network for that. In the customer's application, they could change the parameters that they're monitoring, etc. if they want, but this is a good basic start for a typical customer to get going. Alright, let's get started in the hardware configuration screen, which can be accessed here from this icon at the top of our screen. We're going to be talking about Modbus RTU because it's the most common interface. I'm going to go down to the serial port section and hit the config button. On the XL7 you have a total of 4 CAN ports. You have 3 traditional communication ports and 1 non-traditional one, which you can use by stacking a special CAN board on the back of the unit. MJ2 and MJ3 would be the most typical ports that you would use for doing RS485 Modbus. We're using the MJ2. The first step in this configuration was the application engineer selecting Modbus Master Protocol, and then we've got 3 levels of configuration: the network level, the device level, and the scan list level. Let's start with the network level. The top part of this dialog box here, starting at the left, is all about the communications parameters. RTU Modbus is an RS485 protocol. You need to set your baud rates and parities and stop bits all matching on both sides. So generally I would find out what the default parameters are in the drive and I would have the OCS match those. On the right, you have your choice between Modbus RTU and Modbus ASCII. RTU is by far the most common these days. In this corner, you can slow communications if necessary if you're using an older unit. The next key parameter is timeout. This is the amount of time the OCS is willing to wait for the drive to respond to any kind of query or communications request. I think the default is 5 or 10 seconds, which is too long for an RS-485 connection. I shorten that down to a second or 1000 milliseconds. And then here, this is the number of retries that the OCS will make when it is actually polling the drive over Modbus. So in this case, it'll do 2 retries. So if it tries and is unsuccessful, it'll do 2 more for a total of 3. If the drive is powered down after about 3 seconds, the OCS will take the drive offline. The reacquire time is how long the OCS will take the drive offline for, and I've set it to 4 seconds. We've also recently added the feature to disable either an individual slave itself or Modbus as a whole, but in general I would set the reacquire time at something reasonable. If you have multiple drives on the network, the reacquire time should be 15 seconds to a minute, because while the OCS is not able to talk to that drive, the communications with the other drives will suffer. The next variables we'll talk about is update scan. I like to leave the scan at automatic. That means the OCS is automatically going to handle polling the drive and reading and writing the parameters as they're needed. And if you set the update scan to automatic and the interval to 0, that means the OCS is going to do it as quickly as it can. So it's going to scan all the information that's been configured for, and when it's done with that list, it's going to go back and do it all again. One last note, I talked about the fact that you can assign a variable for disabling Modbus. You can also assign one for getting real-time diagnostics on the communications health over Modbus. On the device level of configuration, we add each drive that we're going to be talking to. In this case, I just have one here. So we can give that drive a name. In this case, I gave it the model number of the drive that we're talking to. You do need to configure a Modbus ID, which typically is between 1 and 247. It needs to be unique and needs to match what the OCS is expecting. And then this is what we were talking about earlier, the style of Modbus address. Modbus 5-digit addresses are by far the most common. 6-digit addressing is more common for Modbus over Ethernet. And if we scroll down a little further, you'll see we've also got some of those generic decimal address and hexadecimal address options that you might find in the back of your user's manual for your drive. If you're not sure, stick with the Modbus 5-digit addressing scheme. It's by far the most common. Okay, here's that disabled variable that you can assign for disabling communications with this particular node on the network. If it goes down, you're going to want to be able to disable that drive and then bring it back on manually using the same variable later on. Then there's additional status information that's geared specifically towards this slide. Lastly, we have what we call a scan list. This is all the data that we're going to be reading and writing on a regular basis. The first thing on the list here is a variable labeled CV_Hertz. So CV, I programmed it to mean control variable for frequency. This is the variable that is going to be sent from the OCS to the drive to control the frequency of the motor. In this particular drive, the ABB ACS 350, that Modbus address in the register map in the parameter map is 40002. So we're going to be writing the frequency value to that 40002. The data is coming from local OCS register 50, which I've given a name of control variable _Hertz. This is labeled as a polled read and write because we're going to be reading the parameter on a regular basis. And then when it changes for control purposes, we're going to write it and then read it back again. You're going to find read-write type options here on the update type. Polled type means that the OCS is automatically going to handle reading and writing this information in the background. There's nothing the user has to do once they've added this value to the poll list or to the scan list. If you only want to do it on demand, you could configure it to triggered read or triggered write, which will then have an additional bit that you'll need to configure to a variable for triggering that read or triggering that write. I usually leave it on polled read and write. Now, let's take a look at another read-write value that's on the list here, the control word. The control word is used by a lot of drives and it typically contains the bit that are used to start or stop the drive, or change direction, forward and reverse, etc. Those parameters are almost always mapped into what's called a control word, and that is, in the case of the ABB drive, mapped to Modbus 40031, and internally on the OCS side, we mapped it to register 53. I was able to map this wherever I want to put it on the OCS side of things. Okay, I've got 50,000 registers to work with. On the drive side, it needs to be put in the right parameter, and again, this is a polar read. Now, let's say that we want to monitor the frequency that the drive is operating with. Well, I'm going to show you how to add another parameter. So I know from my manual that in this particular drive, it has address 40103. That is the actual frequency, and then in my application, I've mapped this into register 55. And this is a read-only type register. Okay, so that's what's required to add parameters to the list. These parameters are spread around. I'm reading and writing one word at 40002 and another at 40103. If I had a series of parameters that were near each other, then I would do a single read instead of reading one register. I might read 16 registers and map them into a group of 16 consecutive registers on the OCS site. That would be far more efficient than having a bunch of entries in my scan list. If there's some information in the middle of that group of 16 that I don't care about, I'll ignore it. The last thing I want to show you is you don't have to have all of your information in the poll list or scan list. So I'm going to go back to the screen that I showed you at the beginning and I'm going to enlarge it. Let's say we want to monitor the current state of the drive, but only when we're on a particular screen on the OCS. We only want to look at it on demand. One option you have is you can add a graphics object to the screen and map it to that particular parameter. The drive is not already mapped, but you can still have it up on the screen. When you're viewing the screen, you'll see the data. When you're not viewing the screen, the OCS isn't paying any attention to the parameter. So let's do that now. I'm going to add a data field. This is going to be a read-only data field. I'm going to be reading current, and it's going to be a decimal value. In the case of the drive, it's going to be giving me 1/10 of an amp. So if it sends back 10.5 amps, it's going to send me 105. My engineering units are going to be in amp, so I'm going to put an entry for that here. Let's make the size of our data a little bigger. For data, instead of polling from internal registers, we're going to poll directly from the ACS 350 that has been configured on a device level via Modbus. Under address, I don't enter in a Horner register. Instead, I'm going to be adding in a Modbus address, which happens to be 40104. I've now configured a data field that will display the current in tenths of amperes. It'll directly grab the data from the drive over Modbus, and it won't map into any OCS register. It won't have it pay any attention to this data or read this data unless the OCS is displaying this screen. And that is the end of our demonstration. Thank you for watching today's tutorial. The Q&A session will begin shortly.
Okay, we have a few questions in. Can we get the program in the presentation? Yeah, that won't be a bother at all. We'll get this video up today, hopefully, and we'll get the program up as well. I'll show you the website there in a second where we'll be putting those. Analog outputs for motor control, which is the best option. We do suggest using 4 to 20 milliamp just because it's the most noise immune. Others should be okay as well, but that is the most noise immune option. Anything else? Not that I can see just now. So just on that, I am going to show you the website. Which I hope you can all see now. So you'll see here on the home screen, we have a banner. I'll just reload it there, so make sure the banner is coming up correctly. Okay, so you'll see here now on the banner, we have our upcoming webinars. You can register for all of them now, they're all live. So they'll be every Thursday for the next 4 weeks. That will be the plan for the next 4 weeks anyway. So it's Modbus and Modbus TCP, on next Thursday coming. And then we'll follow on with the others after that, as we'll see here in a second when the banner comes up. So yeah, we'll have Getting Started with OCS, the Horner I/O review, and then High-Speed Counter review. With regards this presentation and past presentations, we can go to the support bar of the website, and then we can go to the webinars. So along with the banner, you can register for all our upcoming webinars here. They're all lined out for you. And we have all our past webinars here as well. So after this session, we'll pull this down from this and we'll get it uploaded for you as well. Yeah, thank you for joining us this morning. I think that's it. I don't see anything else coming in. Yeah, we would love it if you'd join us again next Thursday for Modbus and Modbus TCP. And if you could join us for the rest as well, that'd be great. That is it for this morning now. Thanks for your time and have a lovely day.